Okay, so here I am back on the website, week 2, looking at creating synthetic data. This is a great lab, partly because synthetic data is really important and partly because it's another good way to learn R. So you'll see me do a lot of what I do, especially when I'm exploring new algorithms, especially in R, is I will go ahead and copy and paste folks' code from usually the web into an R script, and then I'll run it. And if it doesn't work, I might spend a little more time there, or I might go onto someone else's website because I want stuff to work. Okay, so I just ran this now, especially for the stuff you're going to see in class, pulling off the web. Don't just run it. You want to stop, read the material on the web. In particular, take a look. There's questions for us to answer. So if I go back to our studio, and I'll keep bouncing between the two here, you can see that what I've done here is set up a variable. Oh, let's clean some things up first. That'd be good. Easier to see what's going on. Okay, Control L to clear the console. So set up a variable. Num entries is 100. Set that to a vector. Now notice I will call it an array, but you'll hear more of vector for people using R, from people using R. Okay, and then I plot that. Hey, look, nice. All I did was create a vector, and it plotted them, each entry in the array from the start to the end of the array, and that's what index down here means. So it's just indexing the array, and then it gave us our x values. So since we created this as a vector that goes from 1 to 100, we would expect that. Now, let's go ahead and put some random values in another array. So I've set up a variable, our random mean, and then our standard deviation. And now we can call our norm for normal distribution, random normal distribution, with a number of entries, the mean being our random mean, standard deviation being our random standard deviation. And that will give us an array with random values, okay? Now, if we can't see that, we can always say print random values. Our studio will even help us, and there's our values. You can see we've got a whole bunch of values going from, remember, not going from -1 to +1, right? Here's a value that's over 1, okay? Here's one at -2.25. We would expect most of the values to be within one standard deviation, 2/3 of them, but there's going to be ones further out. And they'll become more and more rare, but you might even see a value of 10 or 20 in here. Just very rare to see them. Okay, and on that note, that when we run this again, it's going to generate a different set of random numbers. This is not a true random number generator. It's a pseudo-random number generator, but it is good enough for everything that I do and probably most of the work you're doing. So yeah, each time we run it, you'll see a little different distribution. Now, this shows random data, and it shows pretty clearly. One of the things that I talk to students about is often they look at these clumps and then look at these holes and go, wait, is that random? If it's random, it should have points everywhere. Well, actually, that's uniform or partially uniform. Random data will clump because it's random. In other words, there's a chance of getting a 9. Well, you might get another 9 right afterwards. That would be random. The chance of getting another 9 after a 9 is the same as getting any other value if you're going from 1 to 10. So it might happen, and so you do get clusters and you get holes. So that's pretty common. Okay, so that's that. Let's go back to the website. And now we can look at, oh, what effect does mean and standard deviation have on the data? Well, what we should do there is play with the mean and the standard deviation. Wait, I've lost our studio. There it is. Okay, so what happens when we change the standard deviation? Let's make it 10. Now, it doesn't really look like much change with our graph, but take a look at our y. Right, our y-axis changed quite a bit. Let's make it 1,000. Okay, so our values are much larger in magnitude than they were before, and you can see that up here in our arrays as well. Okay, what happens when we change the mean? I'm going to put my standard deviation back down to, well, let's just go back down to 1. Do a run, whoops, do a run and a plot. Okay, now we're back down to ±1 basically. And let's go ahead and shift our mean to 10. Okay, now notice the middle of our dependent variable is now shifted to 10. So now we've got our data distribution has shifted. Similarly, if we do -10, shifts down. And definitely want you guys to play with this. Now, the other thing you can do is do more values, right? Let's do 10,000 values. Whoa, okay, now you can really see that we've got most of our data within one standard deviation. We've also got tails going off here, so it's 2/3, but there's still a third of it that's out there that's pretty dense. So again, nice thing about R is you can just run lots and lots of numbers pretty quickly. Okay, that's probably a better representation. All right, so fun with R. Okay, so now let's try plotting X against Y. Why would we do that? I don't know. Let's try it. Okay, doesn't look any different. Doesn't look anything different because remember X was just set to a sequence of values from 1 to 100. Okay, that won't normally be the case, but good to know. Okay, so let's create a trend. Again, I'm going to copy the gray code over to RStudio. Now I'm just going to keep going down on this script. You don't want to do this too long, and notice I've already put in some comments for you. But here you can see we're setting up the intercept, beta sub 0, set to 1, slope, beta sub 1, set to 1. Here's our equation of our line, y equals beta 0 plus beta 1 times x. And then we go ahead and we plot that. So let's just do that part. I'm not going to do the last part. So you can see, oh look, we have a pretty strong trend. Great data. We'd love to see this data in the field, but we never will because the only way to get that kind of data is to use a computer to generate it for you. An AB line will then generate a line from using A, an intercept, and B, a slope. Okay, now it's a little bit hard to see. You can see the tail end of it, right? It's a little bit hard to see because our data is so dense. We're going to fix that in a minute. In fact, why don't we go ahead and drop the number of entries here? And again, you can just select it all, run it, and now it's a little bit easier to see that there's a line going through our dots here. If we take it down again to 10, run, you can see that. That's much better. Okay, so what happens if we change the intercept? Notice, again, our intercept changed, but really just the values on the y-axis. What happens if we change our slope? Whoops, have to run the whole thing. Okay, it also doesn't seem to change much. What happens if we make our slope, except for the values on the y-axis? What if we make our slope negative? All right, now it's changing. If we make it larger negative, what's really happening here is these numbers are getting bigger, but remember it's also getting steeper. Even though it doesn't look steeper, it is getting steeper. Just the y-axis is compensating for that. All right, so fun with linear regression. All right, so now what we really want to do is we want to combine our trend. That's our linear regression. And what we've done there is we've created data with a trend. I should make that clear. So this is our trend. In fact, I'll put it back to 1 and 0. That's sort of home base. Okay, so when we do that, we've got a trend here. All right, so there's a trend as this value increases, this value increases. And really from here on, we want to be pretty much plotting X and Y. Okay, so as X increases, Y increases. That's our trend. What we're missing here is the random piece, the noise. So we can go ahead and add some random values into our equation for X, okay? So, well, I should say random. I need to go fix that. I'm just gonna drop that in there and change that to random. Okay, we've got our random values from up here. Now we do have to have all the X's matched, so I'm going to run the whole thing just to make sure. And look, there we go. Now we have some randomness in our data. And for some reason our AB line didn't work. It may be because our random values have such large deviation. I'm going to put the mean back to 0. and run it again, and there's our line. So make sure you have the mean set to 0, standard deviation set to 1 or something fairly small for this experiment. And then you can see what's happening, but then go in and play with them, right? So what does happen when we change standard deviation? Let's make it 2 and run it. Oh, more noise. Okay. In fact, let's really crank up standard deviation. What happens if we get a bunch of noise in our model? Oh, R squareds go down, right? It gets flatter when we have more noise. That is huge. Really important to remember. Okay, now we don't see things where the mean shifts a lot, but let's see what happens when we run it with the mean shifted. Oh, weird. Let's do it more. Let's shift it out to 5. What happens? Oh, look, there's our data and there's our line. I think this is a bad thing, right? And I've seen this happen in real data sets, by the way, when there was a mean and folks didn't know it when they were modeling. Sorry, there was a shift in the residuals and folks didn't know it. And that's what it looked like. Now you guys can spot it. Okay, so I'm also going to crank up the number of entries, and you can hopefully through this see what I'm really looking for you to do is play, try different things, see what happens, get a feel for what all these elements are doing to the data in the model, because this is going to be happening in everything that we do. We're going to have these things. We're going to have one data set that has 10 entries, another that has 1,000,000. What impact does that have on your models? You're going to have different standard deviations for your residuals, definitely. Once in a while, a mean, but not too often. And of course, the equations that you have for your models are going to change. Okay, so definitely play, play, play. Have fun. And I hope this is fun. Okay, now we want to evaluate the trend surface. In other words, we want to create a model. Okay, some of you, this may be the first time you've actually created a model. We haven't actually created a model yet here, right? We've created something that we use to generate fake data. So that's not our model. That's like we're playing Mother Nature saying, here's what this relationship is. We've made this up, and you as the modeler have to figure it out. So creating a linear regression model is not that difficult to do in R. That's it. You just say LM for linear model, Y, and notice that is a tilde. Okay, it's a little bit hard to see. Ooh. Okay, we zoomed in. There we go. A little bit you see. That is not a minus, that's a tilde. And that's saying that we want to model Y using X. And later on we'll add other things besides just X, but this is a straight single linear model. That's all we need. Now, if you run that, it doesn't really appear to do anything except it puts this thing called a model up here with a bunch of stuff in it. Now, you can look at this if you want to, but you don't have to. There's nicer ways to look at it, like print. So we print it. Oh, look, there's our coefficients. Huh. Well, my intercept originally was 0. So it didn't do really good with that. My slope was 1. Hey, there's my slope, 1.0164. That looks pretty good. Okay, so now that just gives us our coefficients or our fitted parameters, estimated parameters, sorry. But we can also do a summary, and now we get all that information plus a bunch of other things, including significance code. So, woo, very significant, yay. Little tiny p-values, so yeah. Solid model. Oh, and look, we're explaining 0.989 of the variance in our data. Well, yeah, we generated the data. Okay, but this is really important now, because what happens when we add more error? So instead of a standard deviation of 30, okay, remember we got 0.98. Oh, and that's regular R squared and then adjusted R squared, which is important later when we get into multiple linear regression. Oh, look what happened to R squared. More error, more noise, more randomness, all those things basically mean the same thing. Suddenly we're explaining less. But notice we have p-value. P-value is fine. If we did this over and over again, we will get basically the same value. That's what p-value tells us. What's the chance that this was a spurious result and we'd never see it again. Well, we're going to see this over and over and over again, basically the same amount. Now remember, we're drawing new random data each time, so it's going to change a bit, but all these R-squareds around 0.5, not very good. And that's really important, right? All we did was change the amount of noise. Drop the amount of noise, boom, great models, great performance statistics, I should say. All right, so same thing will happen with the mean. Let's put this back to 1 so we have like really killer model. Okay, what happens when we change the number of points? Let's change it to 1,000. We get R-squared of 1, which you'll only ever get if you're generating your data with a computer. Okay, so I was like, can't get any better than that. Let's drop it down to 10, see what happens. Ooh, 0.88, not as good. If we keep dropping it down, like let's just do 4, well, all of a sudden, 0.7, you can see what's happening, right? With a little bit of noise, we don't have many points there to put a line through, so things can get wonky really quickly. Okay, 0.56, and this is another reason to chart your data. You can look at that and go, well, that just looks strange. In fact, why isn't that line going through here? I wouldn't expect that. Be ready for strange things to happen. So this is where you'll even hear people talk about how you need to have at least 30 points. Well, there's a reason. About 30 points, you tend to get good models. It's a general rule of thumb, or good analysis from your data, and the potential to get good models. Okay, so hope you're enjoying this as much as I do. There's some questions here for you to answer. But now, next part, also fun, is we get to evaluate our model. So our model is hidden in here, right? If we go ahead and we print our model, there's our model. It's that, in fact, it's really here, right? It's that x equals a plus b times y, or beta 0 plus beta 1 times x. And here's our coefficient. So from that we could actually write the equation y equals 0.1985 plus 0.9916 times x, right? So pretty cool. That's actually our model, but let's evaluate it. So what does that mean? Well, the first step is we have to predict what we think we should get. In other words, I need to make sure this is back at 100 for the number of entries. And I'm going to run everything up to here so we can run the other ones one line at a time. So now we've got some data with a little bit of noise, but not a lot. It's a good place to start. I'm going to create a new array, 0 to 100. Then I'm going to convert that into something called a data frame, which we'll talk a little bit more about in the near future. And now I'm going to use that data to predict my y values. Okay? Whoops. I'm going to click on the right thing. There we go. Now if I plot y, notice that it's linear regression. Right now this is pretty simple. It'll get more complex in a few weeks. Don't worry about that. Okay, again, we've got index. It's just printing out our array values for y. Boom, there we go. Now, the important part is what we can do is we can now compute our residuals. In other words, we can subtract this array from our original quote-unquote data, and that gives us our originals. Okay, now we can histogram our residuals. Sweet! And that should look like it's normally distributed. Okay, so this brings it all back around again, as we've taken our model, we've subtracted our data from our model, the y values, or the dependent variable. That gives us our residuals, and then we histogram our residuals, and this should be a normal distribution or Gaussian distribution. Okay, now there's something else called QQ norm. We'll talk about that in a little bit, but that's another way of evaluating if it looks like our residuals are normally distributed, and this looks really good because it should look fairly linear from lower left to top bottom. Cool? All right. And there is some more stuff on here, polynomials. That's kind of old. We don't really use it much anymore. And I did a section on how to create data with autocorrelated, but I'm not happy with it. The one thing I do want you to do is to have some fun copying this code. Do not worry too much about understanding this code. It's a little complicated. But do start a new R script because we're doing something new now. This is working with two-dimensional data. And want to clear out everything as well. If you don't clear things out, eventually R will start to go slower and have other issues. But I'm just going to select everything and hit run. Okay, now it's going to take a little bit of time, but what it's going to do is basically the same thing we just did for one variable, right? There's our linear regression for one variable, but it did it for two, and you can see there's a slight trend in the other direction. This is kind of a cool 3D package for displaying that. And that package is library RGL. If you need to install that, you can go up here and go quick, where is it? Install packages, and then just type in RGL and install, and that should take care of that, and then add library at the top or just run this code. Okay, so that was, whoop. Uh-oh, I broke something. Which will happen, not usually this soon with something this simple, but it does appear that I broke RStudio. So when that happens, close RStudio, go ahead and save your workspace. Pretty much always do that. It's rare that you have to kill the workspace to get RStudio back once in a while. And then the nice part is this will come right back where you were. Okay? RStudio is great that way. Now, when you get a script working the way you want, you really like it, definitely save it as a scripting file. But when you're playing around like this, you can just keep them as you can see, these aren't actually saved as files. Interesting. For some reason, RStudio is not allowing me to scroll my window using the scroll bars. Okay, well, I won't be using the scroll bars then. We'll figure out something else to do. Okay, so next we want to add a random component to our two-dimensional data. Okay. And again, if I click all, run that. Now we can see what we have is two-dimensional data with a trend and a random component. Two-dimensional data, I should say, two independent variables. We still have one dependent variable. Now we can go ahead and create a model. Run that. Okay, now I haven't done anything to visualize the model, so the output still looks the same, and that's really pretty typical. I have gone ahead and printed and done a summary on the model, so you can see down here that we have coefficients, but now we've got an x1 and an x2, so two independent variables, and we've got intercepts and slopes for that, and then we have our r squared, and now the adjusted r squared becomes important. They're still the same. Great p-value. And I'm going to go back, and now I'm going to plot the model, and you can see this is a little bit complicated. Don't worry about that. You will be writing this kind of R code by the end of class, end of the semester. All right, and with that, a little bit of 3D code, we can see a two-dimensional visualization of a multiple linear regression model. Okay. The model is that surface there, and then we have our data points around it. All right, hope you enjoy this. Play, have some fun with this, and